most of the pollutants from cars actually are emitted in the first 5 to 10 minutes of the car journey before the catalyst has been heated up by the exhaust gases. And so we'd like to get a catalyst for the converter that will work nearer room temperature. The other part of the work is we'd like to actually understand what is happening at the molecular level so that catalysts can be designed by scientific knowledge rather than just by trial and error.
This paper that's come out of Washington State University, Yong Wang and his team, what work have they been doing?
Researchers from 4 different institutions have got together, and one group has made a catalyst of platinum deposited on cerium oxide, and they've done some testing of it and found they could get it to work at reasonably low temperatures, while the other groups have done quite sophisticated analytical techniques to try to understand the chemistry of how the carbon monoxide is being converted. There's been a move towards what's called single atom catalysis. So platinum is a very expensive metal, and usually reactions are carried out on platinum particles. But the only platinum particles that can interact with carbon monoxide are at the surface of the particle. The platinum atoms in the middle of the particle can't contact the carbon monoxide. We're paying for them, but they're being wasted. So we want very small particles, or even just a single atom of platinum. The problem with very small particles is they love to become big particles. Whenever you heat them up, they love to become big particles, and you've lost the advantage. So one role of the cerium oxide is to keep the platinum atoms apart from each other. What the researchers discovered is they managed to prepare single atoms of platinum within the cerium oxide, but they discovered that catalyst didn't actually work very well. The carbon monoxide bound too tightly to the platinum. So they had to heat it up in carbon monoxide at the right temperature. And they found 275 degrees Celsius was the magic temperature for this system. They managed to get 90% conversion of carbon monoxide at just 65 degrees Celsius rather than the usual more than 200 degrees Celsius.
This is the discovery, in essence.
That's a discovery, that's a potential use. Their analytical techniques showed that platinum atoms had actually become small platinum nanoparticles. And the same size platinum nanoparticles were giving different performance for the reaction, depending on the route. Now, they found a high temperature route, where they made it at 800 degrees Celsius, worked the best, because they found the cerium oxide was making a difference. What they think is happening is the carbon monoxide comes down, binds to a platinum nanoparticle, then the oxygen atom that reacts with the carbon monoxide comes from the cerium oxide, not from oxygen molecules in the air.
So you'd usually expect it to come from the oxygen in the air, but it's that support that's then providing this oxygen instead.
Yes, so the support is providing the oxygen atoms that react with the CO, and then it's only later on that the support is regenerated from oxygen molecules in the air reacting with the cerium oxide. So their trick was they found they were able to get the cerium oxide in a nice state, allowing oxygen atoms to transfer from the solid support onto the CO molecule to make it into carbon dioxide.
It's that interaction between the two that's really important. But then also, it's not getting used up. You're saying it regenerates itself.
Yeah. So the importance of this work is they've been able to tune the particle size. You want the platinum particles to be small, but not too small for the right reactivity, and to tune the state of the cerium oxide so that it can easily supply oxygen atoms.
Looking forward then, what's the implications of this work? Using a new interaction, I suppose, for cars and other kind of catalytic converters.
Their new catalyst will be able to be an ingredient within catalytic converters and solve that cold start problem where most of the pollutants are emitted. There are some things that still need to be explored: the cost of the preparation, whether they can do it on large scale, the lifetime. They found their catalysts were stable and could do numerous cycles without deteriorating, but they've only really tested on the matter of days when you want a catalytic converter to work for a year or more to be practical. And there are other things we want catalytic converters to do. So nitrogen oxides, NOx, in car exhaust also needs to be treated as well. It may be possible to combine the researchers' new catalyst and put some extra ingredients onto it that will try to do everything all in one stage. Or it could be part of a separate system where you have effectively 2 or 3 catalytic converters in series with each other in a row.